most important topic in inferential statistics. It is called testing hypothesis. Especially today I'm going to discuss the testing hypothesis for population mean. Let's check what it is. Consider this kind of example. This is the example for testing hypothesis of single population mean. You have seen a cookie bag. It can be chocolate or any kind of cookie. There is some kind of weight indicated in the envelope, in the case. Have you ever suspicious about whether they are enough cookie as indicated in the envelope? Or at the light bulb factory, every year maybe there is a new developed light bulb. And they advertise that it has a longer life. Is it reliable? Is there any way we can check that? Or in this year's academic test, students said there will be an average English score of 5 points higher than last year. How can you investigate this is true? You may check all the population, but that's not easy. Population is too big. Therefore, we'd like to make confirm whether this is true or not by using sample. This is another area of inferential statistics. In chapter 6, we discussed from small sample, we just try to estimate population mean. But here, we have some hypothesis, we call that. We have some hypothesis about the population. In nature, it is provided. You can, as a researcher, you can decide that. What is that hypothesis? Then we decide, suppose there are two types of hypotheses. Which one is right? We call it that is the testing hypothesis. In this textbook, there are three categories. One is test of population mean. Second one is test of population variance. Third one is population proportion. Let's do that, the testing hypothesis of population mean. Let's consider this example. At the light bulb factory, the average life expectancy of a light bulb is known to be 1500 hours, and standard deviation, it is assumed 200 hours. Recently, the company is trying to introduce new production method. They claim that the average life expectancy of 1600. Well, in this situation, we have two types of hypotheses. New method is the same as existing average 1500 hours, or it is more than that, 1600 hours. How can you confirm that? Well, we select a sample, 30 sample, by simple random sampling, and we calculated the sample mean is 1555. Do you think, suppose there are two hypotheses like this, either 1500 or 1600, who make this kind of hypothesis? That is researcher's decision. One of them we call null hypothesis. The other one is alternative hypothesis. We are simply testing hypothesis is we have two hypotheses. Among them, which one you are going to select? But at this point, we usually put the existing some information existing knowledge as a null hypothesis. I'm going to explain it in a minute, why we are doing that. And something new, like new development, we put it in the alternative hypothesis. We want to select one of these. That's testing hypothesis. How we are going to do that? You have a sample mean 1555. It seems middle point is 1550. It is more than that. It looks like it is close to H1. If you don't know statistics, you would say, 15 sample mean is 1555. Therefore, you would select H1. But if you learn statistics, how you make a decision? That is the issue. Again, the null hypothesis, we usually put, we are going to introduce another one in section 7.4. But until that point, we'll assume null hypothesis is existing important thing. Alternative hypothesis is new fact. Therefore, unless there is a significant reason, we try to keep null hypothesis as possible. We call this is conservative decision making. Most of the statistical testing hypotheses based on this conservative decision making. Keep in mind, we emphasize H0 first, null hypothesis. This is common sense. Just compare distance from H0 to H1. You select that. But we learned the statistics, especially we learned the sampling distribution. Statistical testing hypothesis is try to make a decision based on sampling distribution. How you make a decision? Somewhere else between H0, mu 0, H1, we try to have a value we call critical value. Somewhere else in the middle, we try to set up C, critical value, based on sampling distribution. If a sample mean is smaller than C, we'll accept. If not, we'll reject. That's basic idea. Then the issue is how can we select this C? Here's a situation. You have H0, H1. We want to set up some critical value. These are the sampling distribution of all possible sample means. Okay? It is a little exaggeration. It is a very skinny distribution, around 1500. This is a very skinny distribution, around 1600. If H0 is true, we expect this kind of normal distribution. Well, if H1 is true, we expect this is true. What is the exact distribution? Do you remember that? If this is true, all possible sample mean distribution look like this. It's 1500. And then population variance, we assumed that divided by n. If right-hand side is true, we expect this sampling distribution is 1600 sigma square over n. Well, based on this kind of sampling distribution, how you set up critical value? That is the point. If you, can you guess the shaded area, what it look like? Around this area, sample mean comes from the null hypothesis. At the same time, it may come from the alternative hypothesis. This area is overlapped portion. The sample mean comes from H0 or H1? Well, this shaded area imply, suppose sample mean comes from H0, but if it is located around this area, we have to choose H1. That's a mistake. We call that is type 1 mistake. Well, other way around, I mean, this area, what does this mean? There's a possibility sample mean comes from left-hand side or right-hand side. But if it is located here, we have to decide H0 is true. Therefore, sample mean comes from right-hand side, located here. This area is some kind of mistake. We call this is type 2 error. Suppose H0 is important, then we mind about this shaded area. If H0 is true, but sample mean located here, we have to reject. Therefore, it is a mistake. We try to have a small mistake, small type of mistake as possible. Well, usually we set 5% or 1%. It's a researcher's decision. It's some kind of corner point that will make the wrong decision. That is the statistical decision. Critical value comes from how much this kind of type 1 error will allow. We call that is significance level. We usually decide significance level 5%. If you emphasize only H0, well, most of the statistical testing emphasize on H0. Well, you may ignore maybe H1 sampling distribution. Simply speaking, if a sample mean is around here, it's all possibility. That's the difference of someone who didn't take a statistic or statistic. If it is located here, we'll accept. If it is located very far from the center, 1500, we'll reject. Okay. Suppose this is 5%. Can you guess what is this critical line? Because we know this distribution is a normal distribution, is to be 1500 plus 1.645. Do you remember normal distribution theory? And then standard error of this distribution. That's it. This is C. Suppose you have a sample mean. If it is less than this point, it is 15 something, we calculated in. If it is less than this C, we'll accept. If it is greater than this C, we'll reject. Let's see detailed calculation. I explained the type 1 error and type 2 error. I explained until this portion. Suppose you set up significance level as 5%. C is nothing but, since it's sampling distribution when H0 is true, look like this, the C look like this. Our sample mean is 1555. Then what would be your decision? It is less than C. I mean, this critical value is 1560. Therefore, your sample mean is 1555. Therefore, you have to keep H0. You cannot reject H0. Well, that is a little different from common sense. Common sense is just comparing the distance. But here, we are checking possibility. Okay? If it is not corner point, okay? Since H1 is in the right-hand side, we consider this right tail. If it is 5%, that's a significance level. Some allowable range of type 1 error 5%, it becomes 1560. Therefore, sample mean is left-hand side will accept H0. Or you may say, do not reject H0. That is the statistical decision. As we discussed in the sampling distribution, you can have a decision rule in this manner. You may have this expression. Maybe it is easy to understand, but once you are used to it, subtract mean divided by standard error, like this, you may calculate in this manner. Suppose you have sample mean 1555, well, subtract mean, that's H0, mu equal 1500, and divide by standard error. If this transformed standardized value is 1.645, then accept H0, else reject H0. It's the same thing. Since the sample mean is 1555, if you calculate this value, it becomes 1.506. Therefore, it is less than 1.645, we'll accept. In this situation, later we'll use a lot the p-value. What does it mean, p-value? Well, let's go back to this graph. We calculated that this critical value is 1560. But your sample mean is 1555. It is in the a little left of a critical line. What does it mean, p-value? Suppose right tail will be determined for accept reject. Then from the right tail, you calculate probability until sample mean, like this. It means where is the location of sample mean from the right tail. We call that is p-value. Well, why they are thinking about the p-value? In terms of this notation, p-value is it's a probability sample mean greater than 1555. It means location of sample mean from right tail. If you know p-value is very small, that means it is sample mean is located at the corner. That means you have to reject. How small? That's the significance level, 5%. By comparing p-value, it is easy to determine. At the beginning, I explained in this manner, but later, we'll discuss many kinds of testing hypotheses. The computer package will calculate p-value for you. You just make a decision whether p-value is less than significance level or not. If it is less than, that means it is a very far corner by considering H0. Therefore, reject H0. Here's a summary. In case of testing hypothesis, we'll consider, you may do that directly calculation the critical value, but as we discussed here, this kind of normalization, once you are used to it, it is more convenient. Since you know some of the normal value, you just compare that. Let's say if it is alpha 5%, calculate normalized value of sample mean. If it is 1.645, reject. Suppose the H1 is in the left corner like this. This is general expression. Okay? Since we are considering H0 is important, all this type mu equal greater than some value mu0, they belong to this kind of decision rule. Suppose the hypothesis H1 is in the left tail, then the standardized value we are checking less than minus 1.645 like that, in case of 5% alpha. In case of two-sided, whether mu equal mu0 or not, we are considering both sides 2.5% in case of alpha 5%. If it is located one of two areas, 2.5%, we consider it is far from H0. This is general rule. But you'd better understand this first. Okay? If you understand this concept, maybe it is not a problem. Well, if it is p-value, the p-value is less than significance level, you will reject. How you calculate? In case of right-hand side, H1 is greater than, it's a right tail test, we call that. We just calculate location of sample mean from the right-hand side. That's this notation. Well, in case of left tail test, we are considering from the left-hand side to your sample mean. In case of two-tail test, we are considering one of them, we calculate the location of sample mean, either right tail or left tail, which one is more smaller, then we just multiply 2. Rather than remember this formula, you'd better understand it. Understand the concept, maybe it is simple. One more thing, remember when chapter 6, if population standard deviation is known, we use the standard normal distribution. But if we don't know about the population standard deviation, we have to use sample standard deviation like this. At that time, we have to use T. Same concept. I mean, this statistic follows T. Therefore, in case of a right tail test, we are considering T distribution. And if it is right tail 5%, if standardized value is greater than p-value 5% right tail, we will reject. In case of left tail, we consider left tail alpha %. If it is less than that, it is rejected as 0. In case of two-sided, we are considering, both 2.5% each. If it belongs to that area, we will reject. These are the old theory of testing hypothesis. Let's consider example. Suppose you have a cookie bag. They are supposed to be 250 grams. Well, you collect 100 sample. And somehow sample mean is 253. Suppose you know the standard deviation, it means population standard deviation. Then how can you test that? You can use standard normal distribution. How can you do that? Well, this is sample mean and normalized value. If it is alpha 1%, it should be 2.5 or 2.33. The calculated value is 3. The location of sample mean transformed value is 3. It exceeds 2.326. Therefore, H0 is rejected. P-value is location of the sample mean, but the transformed value, you already calculated that. What is the value from the right tail to this 3? In case of this normal distribution, when H0 is true. Well, you normalize the value that is already 3. Therefore, if you calculate this, it is just 0.1%. Suppose you have this kind of two-sided test. Then you have to considering the both side. Well, in case of 99%, I mean corner point is 1%, 0.5% each. This critical value is 2.575, but this is normalized value of sample mean is 3. Therefore, H0 is rejected, same thing. P-value is you calculate one of the tail probability. 3 is located in the right tail. Therefore, you calculate this probability, multiply 2. You can do that using E-stat. Okay. Let's do experiment. Are you ready to use E-stat? Click E-stat U. And where is the testing hypothesis? Here is testing hypothesis about mu. Okay. We will have this problem. Well, suppose in case of first example, you want to test that H0 was 1500, right? And then alternative hypothesis, whether it is 1500 or 1600, but it is the same decision rule, you select this. Suppose you know population standard deviation. At that time, we know that, therefore, you have to use a standard normal distribution. Sigma square, we have sigma 200, therefore, 200 times 200, it is 40,000, right? Let's consider alpha equal 5%. And sample size it was 30. The sample mean was 55. You don't need sample variance. We assume the population variance. Therefore, if you execute, they provide this. Okay. What does this mean? Your sample mean, the transformed value of your sample mean is located here. Critical value is a little above that. Therefore, you have to accept H0. Okay. Using this E-stat new module, testing hypothesis is simple. Similarly, you can do like this. I demonstrate in the example already. You don't understand immediately. In this case, you just plug in this number like this. Then click execute button will generate this one. It exceeds the critical line. In case of a two-sided test, you just click this radio button. Well, they're gonna check both sided. What's next? Suppose you have a small sample size. That means in case of a small sample size, you have to use sample variance. Okay. Then in that case, they provide you T distribution. You have to use T distribution. And well, we did a similar calculation, and H0 is accepted. Well, p-value can be calculated similarly as G distribution. In case of a right tail, it's a location of sample mean But in case of T, you need the standardization and check it from the right tail. Here's the East and New module. If you are using that, why don't you practice it by yourself? You can check that it is accepted. Well, not only the sample mean you may insert there, you can insert this kind of numbers. Okay? It is the same thing. You want to test there whether mean is 175 or not. If you don't know standard deviation, population standard deviation, you have to use T. Let's look at what it could like. Let's refresh this module. Well, you want to test there. Its height is 175. Okay? And what was the alternative hypothesis? Or greater than. Then you have to select what? You have to select greater than alternative hypothesis. Yeah, you can choose a t-test. You may choose alpha 5%, 1%. Click this execute button. You calculate the confidence interval and corresponding the t-distribution testing hypothesis. That's it. Here's the output, same thing. Okay. You may use the e-stat, not e-stat U. You may use e-stat and plug in data like this. You can use in this module. You can do either e-stat or e-stat U. This example shows you e-stat practice. I just showed you this is e-stat U module. Okay, I hope you understand this testing hypothesis. It is so important. Please read the textbook and practice it several times. Okay, see you next time. Bye-bye.